Hello students, so in this lecture we shall be discussing about nucleation and growth. And we will first start with especially this nucleation and growth in thin films, and we will study it in terms of substrate temperature. Now at low substrate temperature, mm, call it as Ts. So at low Ts, what we get is a very high supersaturation critical nucleus. Super saturation, and we all know that there is when there is an nucleation and growth taking place, there is a first the nucleation of the crystallites, the nucleides are formed, and when the radius and they start to grow by attracting atoms towards each other, and when at a certain point of time, when the radius is greater than critical radius, then only these nucleides growth take place. Else if R is less than the critical radius, then they again dissolve into the main solution, solid solution. Now, you know, at very low substrate temperature, so we have assumed that Ts is very low. So in this case, we assume the critical nucleus to be consisting of maybe only a single atom, because unless and until you are supplying certain amount of heat, that is temperature, it cannot attract more atoms toward itself. Now, when there is a critical nucleus of a single atom, what it will do, it will form a pair with another atom. And by random occurrence, to become stable cluster can grow spontaneously, and to become a stable cluster, and after that grow spontaneously. Now the stability of a pair is again on this slide. Stability of a pair is again derived from uh, assumed bond per atom. But bond per atom. And at high Ts, the pair is not stable. Pair is not a stable cluster because the atom will have more vibrations due to the high temperature. So what it will do to attain stability again, it will attract one more atom. So initially it was one single atom. To attain stability, it has done. It has invited one more atom to it itself. Now again the temperature has risen up, so this is also not very stable. So what it will do, it will try to attract another atom, and again the next step is it will try to attract another atom. So the number of atoms keeps on increasing as the cluster tries to attain stability. Now this is actually what is known as nucleation. So we can see that the nucleation rate is proportional to something called n star into gamma, where n star is the number of atoms, so the star is written because it is in not a fixed quantity, it keeps on increasing. And we will tell what is gamma is. So first of all, let us assume that En is the energy dissociate energy to dissociate n add atoms. Add atoms are those atoms which are in the process of making a film, and obviously they are adsorbed on the surface. They are on the surface, and so now as the size of the cluster increases, that means as n star increases, that means n star changes to say n star plus 1, then the nucleation rate will also increase, and nucleation rate and temperature dependent increases as, so nucleation rate and temperature dependence will increase as r to the power n star plus 1, and so we obtain an expression gamma is equal to minus Q dissociation energy plus half into e to the power n divided by K ln R by nu. NO is the initial number of atoms, and nu is another constant. R, as you know, is the gas constant, and K is again the Boltzmann factor or Boltzmann constant. So the nucleation theory is also given by, or the nucleation rules for that matter, are also given by capillary and atomistic theories. Whereas this is valid only when the density of the nuclei reaches is max. Now the average distance between the nuclei is the mean diffusion distance. So after the mean diffusion distance has been achieved, the nuclei will grow by capturing atoms by diffusion. And this process does not allow further nucleation to take place. Now, the saturation density of nuclei is again independent of the impingement rate provided. This is independent of impingement rate. That means the rate at which the atoms are coming and hitting the substrate. That is the impingement rate. And this gamma is actually the impingement rate that we talked about. The impinging atoms equilibrated in stability, and the effect of also the momentum of the vapor is not significant. And impingement rate is smaller than the atom diffusion rate, so the equilibrium condition exists. So this gamma is actually less than atom diffusion rate, which actually leads to equilibrium. Now, under this condition, the saturation density that we were talking about, when the impingement rate is less than the saturation density decreases with substrate temperature. saturation density is n is equal to n0 exponential minus q dash minus qd by kt. Where qd is the dissipation energy and qt is the association energy, and it will be q dash minus qd by qt. And at steady state, this is all about saturation density, and steady state is attained in this case when everything is in equilibrium after something called an induction period. And what do we mean by this induction period? Induction period is basically the sum of the times necessary for that atom to attain the population in kinetic equilibrium. So let's write it and understand. So induction is basically the sum of the times necessary for our atoms to attain population. For atoms to attain population in kinetic equilibrium. Now, after this induction period is over, then the nucleation density. So after we call it as T I. After this induction period is over, the nucleation density. The nucleation density increases rapidly. To approach, it will increase at a very high rate. To approach saturation, towards saturation. Now, the saturation density of uniformly distributed ions of metals. So let's consider that it's a uniformly distributed ions of metals which have got a comparable melting point. So that uniform distribution, due to that uniform distribution, the saturation density is approximately equivalent to the power 10 to 10 to the power 12 atoms per centimeter square. Now, after reaching the saturation, the ion density decreases. Comes down and comes down with deposition rate, with deposition rate and substrate temperature Ts, and there is and also with subsequent film growth. If there is film growth also taking place, then also the ion density will come down. Now, if we compare sputtered and evaporated films, then the rate of decrease uh, of the saturation density is much rapid with sputtered uh, films than compared to evaporated films. And also there is increased smoothness with temperature. Now, this induction period, as we mentioned earlier, this induction period, or we can say TI, this is basically the time lag uh, that is occurring between the time of deposition and the observation of condensation. So the time taken, so this is substrate. There is a certain time uh, in which the atoms all come to the substrate, and there is a certain time when these start to attach oneself with another to form the film. The time lag between these is the induction period that we have mentioned. Now, the nucleation growth stage is affected if the substrate is related with energetic atoms. Now, before why does this rate of decrease is more rapid in sputter? This is what has been explained here. So, in case of sputter, what happens is that the energetic atoms, they hit the surface of the substrate. This is the substrate, and due to this heating, uh, the nucleation growth stage is affected, since the electrostatic charge should facilitate condensation by lowering nucleation barrier. So, since electrostatic charges should facilitate condensation by lowering nucleation barrier. Now, it has been observed that the nucleation is very rapid, or it has more tendency to occur at the defects, at surface defects like ledges, monoatomic steps, etc., etc. Now, why this is more active in these defects is the reason because of the lower nucleation barrier increased kinetic energy. The reason for this observation is lower nucleation barrier and increased binding energy. This is specifically the cases for these defects. That is why it helps the nucleation process. Now, for metals, for example, if we're talking about, say, metals like bismuth, antimony, lead, silver, gold, copper, aluminum, etc., The substrate temperature here is usually greater than two-thirds of, or we should say the saturation temperature, not the substrate temperature. Ts is actually saturation temperature. Since we have mentioned substrate temperature as with Ts, let's write it St. St when greater than 2-3 Tm, which is the melting temperature, then we can have different saturations. For example, uh, this is for solid, or it's not actually saturation when the solid actually forms. Now, film condensation occurs while vapor, solid, and liquid transformation. So, film condensation is a correlation between vapor, solid, and liquid. The film condensation occurs by vapor to sorry vapor to liquid to solid transformation, and for substrate temperature Ts less than two-thirds Tm, vapor solid transformation takes place, and if Ts is less than one-third Tm, Tm is the melting point, then vapor to liquid to amorphous solid will take place, and one-third one-third of the melting point is the limit, below which the atoms don't have sufficient mobility. Atoms don't have sufficient mobility. And for two-thirds M, for this case, that means 2 by 3 Tm, as is close to Tm. So in this case, the melting point of a spherical crystallite of radius r is depressed because work pressure inside is increased inside the curved surface. So the melting point of an island, which is considered to be spherical in nature, is lowered. The reason is because of the increased vapor pressure inside the curved surface. So based upon this, the lowered melting temperature is equal to the original melting temperature exponential minus 2 sigma V by LR, where sigma is the solid liquid interfacial energy, L is the latent heat of fusion, V is the molar volume of the solid. This difference in temperature between the original and the decreased melting point is delta T, and this delta T is again to the sigma by R to Tm by L into V, as is the radius of the nucleus. So the smallest R is basically the critical nucleus. Smallest is basically the critical nucleus. And the expression relating Tm and Tr is equal to 1 plus sigma by sigma critical energy into K into Tm by L ln vapor pressure by vapor pressure equilibrium. In this expression, if K Tm by L is close to 1, that means we're talking about this part, this one. If this is taken as 1, then and sigma by sigma critical is 0.1. That means talking about this one, this is 0.1. So what he is telling is that this part is 0.1 and this part is equal to 1. So what is remain is Tm by Tr Tm by Tr is equal to 1 plus 1 by 10 into ln P by Pe. This is the expression for Tm by Tr, the reduced melting point and the original melting point for the critical nucleus. And for large number of metals, formation of close packed structure takes place due to this like in FCC and HCP. So formation of close packed structure takes place due to these two conditions.